An aspheric lens or asphere is a lens whose surface profiles are not portions of a sphere or cylinder. In photography, a lens assembly that includes an aspheric element is often called an aspherical lens. The asphere's more complex surface profile can reduce or eliminate spherical aberration and also reduce other optical aberrations such as astigmatism, compared to a simple lens. A single aspheric lens can often replace a much more complex multi-lens system. The resulting device is smaller and lighter, and sometimes cheaper than the multi-lens design. Aspheric elements are used in the design of multi-element wide-angle and fast normal lenses to reduce aberrations. They are also used in combination with reflective elements such as the aspherical Schmidt corrector plate used in the Schmidt cameras and the Schmidt-Cassegrain telescopes. Small molded aspheres are often used for collimating diode lasers. Aspheric lenses are also sometimes used for eyeglasses. Aspheric eyeglass lenses allow for crisper vision than standard best-form lenses, mostly when looking in other directions than the lens optical center. Moreover, the reduction of the magnification effect of a lens may help with prescriptions that have different powers in the two eyes. Not related to the optical quality, they may give a thinner lens, and also distort the viewer's eyes less as seen by other people, producing better aesthetic appearance. Surface profile. While in principle aspheric surfaces can take a wide variety of forms, aspheric lenses are often designed with surfaces of the form where the optic axis is presumed to lie in the z direction, and is the the z component of the displacement of the surface from the vertex, at distance from the axis. The coefficients describe the deviation of the surface from the axially symmetric quadric surface specified by and. If the coefficients are all zero, then is the radius of curvature and is the conic constant, as measured at the vertex. In this case, the surface has the form of a conic section rotated about the optic axis, with form determined by. Unfortunately, the above equation suffers among others from strong correlation between the coefficients of the first term in the polynomial terms. This leads to strong divergences when it comes to fitting the equation to an aspheric surface. Therefore different equations using Q polynomials, where coefficients are orthogonal to each other, are an alternative that is sometimes used. Manufacture. Small glass or plastic aspheric lenses can be made by molding, which allows cheap mass production. Due to their low cost and good performance, molded aspheres are commonly used in inexpensive consumer cameras, camera phones, and CD players. They are also commonly used for laser diode collimation, and for coupling light into and out of optical fibers. Larger aspheres are made by grinding and polishing. Lenses produced by these techniques are used in telescopes, projection TVs, missile guidance systems, and scientific research instruments. They can be made by point contact contouring to roughly the right form, which is then polished to its final shape. In other designs, such as the Schmidt systems, the aspheric corrector plate can be made by using a vacuum to distort an optically parallel plate into a curve, which is then polished flat on one side. Aspheric surfaces can also be made by polishing with a small tool with a compliant surface that conforms to the optic, although precise control of the surface form and quality is difficult, and the results may change as the tool wears. Single-point diamond turning is an alternate process, in which a computer-controlled lathe uses a diamond tip to directly cut the desired profile into a piece of glass or another optical material. Diamond turning is slow and has limitations in the materials on which it can be used, and the surface accuracy and smoothness that can be achieved. It is particularly useful for infrared optics. Several finishing methods can be used to improve the precision and surface quality of the polished surface. These include ion beam finishing, abrasive water jets, and magnetorological finishing, in which a magnetically guided fluid jet is used to remove material from the surface. Another method for producing aspheric lenses is by depositing optical resin onto a spherical lens to form a composite lens of a spherical shape. Plasma ablation has also been proposed. The non-spherical curvature of an aspheric lens can also be created by blending from a spherical into an aspherical curvature by grinding the curvatures off-axis. Dual rotating axis grinding can be used for high-index glass that isn't easily spin-molded, as the CR39 resin lenses. Techniques such as laser ablation can also be used to modify the curvature of a lens, but the polish quality of the resulting surfaces is not as good as those achieved with lapidary techniques. Standards for the dispensing of prescription eyeglass lenses discourage the use of curvatures that deviate from definite focal lengths. Multiple focal lengths are accepted in the form of bifocals, trifocals, varifocals, and cylindrical components for astigmatism. Ophthalmic uses. Like other lenses for vision correction, aspheric lenses can be categorized as convex or concave. Convex aspheric curvatures are used in many presbyopic varifocal lenses to increase the optical power over part of the lens, aiding in near-pointed tasks such as reading. The reading portion is an aspheric progressive ad. Also, in aphakia or extreme hyperopia, high-plus power aspheric lenses can be prescribed, but this practice is becoming obsolete, replaced by surgical implants of intraocular lenses. Many convex types of lens have been approved by governing agencies regulating prescriptions. Concave aspheres are used for the correction of high myopia. They are not commercially available from optical dispensaries, but rather must be specially ordered with instructions from the fitting practitioner, much like how a prosthetic is customized for an individual. The range of lens powers available to dispensing opticians for filling prescriptions, even in an aspheric form, is limited practically by the size of the image formed on the retina. High-minus lenses cause an image so small that shape and form aren't discernible, generally at about -15 diopters, while high-plus lenses cause a tunnel of imagery so large that objects appear to pop in and out of a reduced field of view, generally at about +15 diopters. In prescriptions for both far-sightedness and nearsightedness, the lens curve flattens toward the edge of the glass, except for progressive reading ads for presbyopia, where seamless varifocal portions change toward a progressively more plus diopter. High-minus aspheres for myopes do not necessarily need progressive ad portions, because the design of the lens curvature already progresses toward a less-minus more plus dioptric power from the center of the lens to the edge. High-plus aspheres for hyperopes progress toward less plus at the periphery. The aspheric curvature on high-plus lenses are ground on the anterior side of the lens, whereas the aspheric curvature of high-minus lenses are ground onto the posterior side of the lens. Progressive ad reading portions for plus lenses are also ground onto the anterior surface of the lens. The blended curvature of aspheres reduces scotoma, a ringed blind spot. Non-optical advantages: high-minus lenses, especially finished in a plastic resin lens, have dangerously curved edges that do not bevel off sufficiently to protect the eye from injury. Serious injury to the eye is often seen from blunt trauma, when the edge of a thick lens has been mounted in a poorly fitted frame. The concave lens design is different from the usual best form curvatures ordered in low-power thin lens prescriptions, but by splitting the curvature in thirds or so, a thinner high-minus lens is developed, although costing more, and more difficult to dispense. History. In 984, Ibn Zal first discovered the law of refraction, usually called Snell's law, which he used to work out the shapes of anaclastic lenses that focus light with no geometric aberrations. Early attempts at making aspheric lenses to correct spherical aberration were made by René copyright Descartes in the 1620s, and by Christian Huygens in the 1670s. The cross-section of the shape devised by Descartes for this purpose is known as a Cartesian oval. The Visby lenses found in Viking treasures on the island of Gotland dating from the 10th or 11th century are also aspheric, but exhibit a wide variety of image qualities, ranging from similar to modern aspherics in one case to worse than spheric lenses in others. The origin of the lenses is unknown, as is their purpose. Francis Smethwick ground the first high-quality aspheric lenses and presented them to the Royal Society on February 27, 1667/8. A telescope containing 3 aspheric elements was judged by those present to exceed a common, but very good telescope in goodness, by taking in a greater angle and representing the objects more exactly in their respective proportions, and enduring a greater aperture, free from colors. Aspheric reading and burning glasses also outdid their spherical equivalents. Moritz von Ruhr is usually credited with the design of the first aspheric lenses for eyeglasses. He invented the eyeglass lens designs that became the Zeiss punctal lenses. The world's first commercial, mass-produced aspheric lens element was manufactured by Elgate for use in the Golden Navitar 12mm/1.2 normal lens for use on 16mm movie cameras in 1956. This lens received a great deal of industry acclaim during its day. The aspheric elements were created by the use of a membrane polishing technique. Testing of aspheric lens systems. The optical quality of a lens system can be tested in an optics or physics laboratory using bench apertures, optic tubes, lenses, and a source. Refractive and reflective optical properties can be tabulated as a function of wavelength, to approximate system performances. Tolerances and errors can also be evaluated. In addition to focal integrity, aspheric lens systems can be tested for aberrations before being deployed. See also, hyperbola, parabola, radius of curvature, references, AB, what do aspheric, or aspherical mean? So look lens optics. Retrieved June 15, 2012. Meister, Darrell. Ophthalmic lens design. Opticampus.com. Pruss, Christoph. AL testing aspheres. Optics and Photonics News 19, 26. Bibcode 2008 OPT-PN 19. 26H DOI, 10.1364/OPN. 19.4.00026. Forbes, Greg. Shape specification for axially symmetric optical surfaces. Opt. Express 15, 5218 Euro 5226A, ABC Shorey, Arik B. Galini, Don. Kordonski, William. Surface finishing of complex optics. Optics and Photonics News 18, 14 Euro 16 Jaley, Mo. Ophthalmic lenses and dispensing. Elsevier Health Sciences. PA 178. ISBN A0-7506-5526-7 Wolf, KB Geometry and Dynamics in Refracting Systems. European Journal of Physics 16, 14 Euro 20 Rasht, R.A. Pioneer in Anaclastics, Ibn Zal on Burning Mirrors and Lenses. ISIS 81, 464 Euro 491A, A.B. Schmidt, Olaf. Karl-Heinz Wilms, and Linchelbach. The Visby Lenses. Optometry and Vision Science 76, 624 Euro 630 doi, 10.1097/0006324-1999000-00019A, ABC. An account of the invention of grinding optic and burning glasses, of a figure not spherical, produced before the Royal Society. Philosophical Transactions of the Royal Society 3, 631 Euro 2. 1668. doi, 10.1098/STL. 1668.0005. Retrieved April 4, 2012. A.